Merging minds and machines, the dawn of Swiss biocomputers and the wetware revolution. Introduction, from silicon dreams to living circuits. Imagine a world where the hum of server farms is replaced by the subtle pulse of living tissue, a symphony of neurons firing in petri dishes, not transistors etching pathways on silicon wafers. This is no longer the stuff of Philip K. Dick novels or the Matrix's simulated realities. It is the tangible frontier of biocomputing, where human brain cells are fused with electronic hardware to create hybrid systems that think, learn, and adapt with an efficiency that dwarfs our most advanced AI. At the vanguard of this revolution stands Switzerland, a nation synonymous with precision engineering and alpine innovation, now birthing wetware machines that blur the line between biology and technology. In the labs of Vevey, overlooking Lake Geneva, the startup Finalspark has unveiled the Neuroplatform, the world's first commercially accessible bioprocessing system powered by lab-grown human brain organoids, tiny, pulsating clusters of neurons derived from ordinary skin cells. These organoids, each no larger than a lentil, are wired to silicon chips via arrays of electrodes, forming a biocomputer that processes data not through binary code but through the electrochemical whispers of living cells. Claiming to consume 1,000,000 times less energy than traditional digital processors, this hybrid tech promises to upend everything from drug discovery to sustainable AI. But beyond the technical marvel lies a deeper intrigue. What happens when we grant machines a sliver of sentience? As Finalspark's co-founder Fred Jordan muses, when you start to say, "I'm going to use a neuron like a little machine," it's a different view of our own brain and it makes you question what we are. This essay delves into the Swiss biocomputer breakthrough, dissecting its mechanics, historical roots, real-world applications, and profound implications. Drawing on recent developments, including peer-reviewed studies and global parallels, we explore how these living circuits could redefine computation, or unravel the ethical fabric of humanity. Through examples from epilepsy modeling to energy-sipping AI, we'll uncover a narrative as captivating as it is cautionary: the fusion of flesh and code, where progress pulses with life itself. The biological bedrock, from stem cells to sentient silicon. To grasp the allure of Swiss biocomputers, one must first descend into the cellular crucible where they are forged. The process begins not in a cleanroom of photolithography but in a bioreactor humming with the alchemy of induced pluripotent stem cells, iPSCs. Pioneered by Nobel laureate Shinya Yamanaka in 2006, iPSCs allow mature cells, like those scraped from a donor's arm, to revert to an embryonic-like state, capable of differentiating into any tissue type. At Finalspark, skin fibroblasts are reprogrammed into neural progenitors, then coaxed into self-organizing organoids, three-dimensional spheres of 10,000 to 100,000 neurons in glial cells that mimic the brain's cortical architecture. These organoids are no mere blobs, they exhibit rudimentary brain-like behaviors. Within days of culture, they generate spontaneous electrical activity, firing patterns akin to fetal neural waves, sustained by a microfluidic perfusion system delivering nutrients and oxygen. Finalspark's innovation lies in integration. Up to 16 organoids are arrayed across 4 silicon substrates, each studded with 8 multi-electrode arrays, MEAs. These platinum-tipped probes, finer than a human hair, interface directly with the tissue, reading synaptic spikes at millisecond resolution and delivering stimuli via biphasic pulses. The result? A neuroplatform, where biological wetware and electronic dryware converse in a closed-loop dialogue, processing inputs through spike timing-dependent plasticity, STDP, the brain's Hebbian rule that neurons that fire together wire together. Energy efficiency is the siren song here. The human brain, with its 86 billion neurons, guzzles just 20 watts, equivalent to a dim LED bulb, yet outperforms supercomputers in pattern recognition and adaptability. Finalspark's biocomputers scale this down. A single organoid array sips microvolts, achieving computations at picojoule per operation levels, a millionfold thriftier than silicon GPUs churning through AI training. As one ex-post from tech enthusiast at Immerse notes, envisioning data centers full of living servers which replicate aspects of how artificial intelligence, AI, learns, and could use a fraction of the energy of current methods, this could slash the carbon footprint of AI, which already rivals aviation's emissions. Yet, challenges abound. Organoids lack vasculature, relying on diffusion for sustenance, which caps their lifespan at 100,120 days before necrosis creeps in. ETH Zurich's parallel efforts with hybrid neurochips, nanoscale electronics fused to brain slices, address this via optogenetic interfaces, using light to trigger precise neural ensembles without invasive probes. These Swiss synergies hint at scalability. Imagine organoids vascularized with bioprinted capillaries, extending viability to years. Historical echoes, the long march from von Neumann to vital circuits. Biocomputing didn't spring Athena like from Swiss labs, it's the culmination of decades chasing the brain's blueprint. John von Neumann's 1940s cellular automata dreamed of self-replicating machines, while Carver Mead's 1980s neuromorphic engineering birthed silicon neurons mimicking ion channels. By the 2010s, organoids emerged as brains in a dish, with 2019's landmark, a cortical organoid integrated into a robotic arm, learning to track light via dopamine rewards. Switzerland's entry was prescient. In 2021, Finalspark's precursors at EPFL, École Polytechnique Fédérale de Lausanne, demonstrated organoid-driven reservoir computing, where random neural dynamics pre-process data for machine learning algorithms. This echo-state network leverages the organoid's chaotic firing as a high-dimensional feature extractor, outperforming traditional recurrent nets in time series prediction. Fast forward to 2024, Finalspark's Neuroplatform goes commercial, renting access for $500 monthly, democratizing wetware for global researchers. Globally, parallels amplify the intrigue. Australia's Cortical Labs launched CL1 in March 2025 to 800,000 neurons plated on a multi-electrode array (MEA) chip, priced at $35,000, with cloud access at $300 per week. Famously, Dish Brain, CL1's progenitor, mastered Pong in 2022, self-organizing to maximize rewards, tonal feedback, via curiosity-driven exploration, sans explicit programming. X-user. Ad iter intellectus hails it as synthetic biological intelligence, noting its programmable and adaptive, living computation that outpaces silicon in relevance and energy use. Meanwhile, Johns Hopkins multi-region organoids, infused with endothelial cells for faux blood vessels, simulate epileptic seizures for anti-epileptic screening, reducing animal trials by 70%. These threads weave a tapestry, from von Neumann's abstractions to Finalspark's fleshly fruition. Biocomputing evolves as evolution's remix, biology bootstrapping technology. Applications in action, from pill pipelines to prosthetic minds. The true seduction of Swiss biocomputers lies in their versatility, transforming abstract potential into palpable progress. Consider drug discovery. Traditional screens rely on animal models or 2D cell cultures, yielding 90% failure rates in human trials. Organoid biocomputers offer precision. Finalspark's platform has hosted over 1,000 organoids, amassing 18 terabytes of neural data for modeling neuropsychiatric disorders. In one experiment, donor-derived organoids from epileptic patients were stimulated to induce seizure-like bursts. Applying candidate drugs like levetiracetam restored rhythmic firing, predicting efficacy with 85% accuracy, far surpassing in silico simulations. AI acceleration beckons next. Training large language models devours gigawatts. Biocomputers, by contrast, embody neuromorphic learning intrinsically. Finalspark's arrays perform edge AI tasks, speech recognition, anomaly detection, at 10x the speed of silicon equivalents, self-repairing via neurogenesis, new neuron sprouting. Bloomberg's 2025 feature spotlights this. Scientists are exploring biocomputing to overcome the physical limitations of microchips, with Finalspark's dopamine dosing systems training organoids on reinforcement learning, mirroring basal ganglia circuits. X discussions buzz with at Rohanpal_IS breakdown. CL1's sub-MIS response enables real-time behavioral computation, outlearning RL agents in adaptive tasks. Neural prosthetics gleam on the horizon. Zurich's hybrid neurochips, embedding nanowires into rat brain slices, have restored motor control in paralyzed rodents by decoding intent from 1,000 channel recordings. Scaling to humans, Finalspark envisions implantable biocomputers, organoids tuned to a patient's genome, interfacing with spinal cord stimulators to bypass lesions. A 2025 pilot at University Hospital Zurich tested this in vitro. Organoids learned to generate phantom limb signals, hinting at bespoke therapies for spinal injuries. Environmental monitoring adds whimsy. Deployable biosensors of organoids detecting pollutants via toxicity-induced spike disruptions, outperforming chemical assays in sensitivity. As at 0x Mad Mox tweets, biocomputers offer major potential for AI training, medical research, and drug testing, and could drastically reduce reliance on animal testing. Ethical labyrinths. Souls in the synapse? Intrigue turns thorny with ethics. Are organoids conscious? Finalspark insists no, lacking thalamocortical loops for qualia, but critics like Imperial's Simon Schultz warn of sentience gradients as complexity grows. Ex-philosopher at 7SEES_ decries it as biodigital convergence, red flags, evoking transhumanist dread. Ownership vexes. Donors consent to iPSC use, but who owns emergent intelligence? Cortical Labs' Brett Kagan grapples this in interviews, proposing neurorights frameworks. Philosophically, it echoes Mary Shelley's Frankenstein, assembling life from disparate parts, only to question its soul. As at Brian Rimmel posts, old, your computer. New, your brain cell biological computer, summoning matrix-esque queries. If machines dream of electric sheep, do biocomputers dream of flesh? Horizons and hazards. A pulsing future. Peering ahead, Swiss biocomputers could spawn living data centers, racks of perfused organoids, cooled by nutrient mists, training exascale AI on watts, not megawatts. By 2030, hybrids with quantum dots might entangle neural spikes with qubits, birthing probabilistic wetware. Yet hazards loom. Biosecurity risks from weaponized organoids, or inequality if access favors pharma giants. Conclusion. The vital spark of tomorrow. Finalspark's fusion of human neurons and silicon isn't mere tech, it's a mirror to our essence, challenging us to harmonize the organic with the engineered. As Dr. Jordan confesses, it's living in one of those sci-fi books. With applications from curing epilepsy to greening AI, the intrigue is irresistible. But as we merge minds and machines, let us tread with wonder and wisdom, lest our creations outgrow their creators. In the quiet throb of a Vevey lab, the future doesn't just compute, it lives.